Power usage effectiveness is a core KPI in serious data centers. In Bitcoin mining, where energy is the business model, it is arguably even more important. Yet, many miners don't fully understand it. Let's change that. In this video, I will explain what power usage effectiveness is, how it is calculated, and I will provide some economic examples of why it matters. We will first talk about what is power usage effectiveness. Then I will lay out the different drivers of power usage effectiveness. I will explain how it impacts mining profitability with a real economic example of that. And in the end, we will go through how miners can optimize the power usage effectiveness of their sites. What is power usage effectiveness? Power usage effectiveness, or PUE, is a measurement of the energy efficiency of a data center. In a data center, you basically have two types of power consumption. You have total facility power and IT power. Total facility power is the power consumption of the entire facility. That is all the components of the facility. Server power, so IT power, cooling, power losses, and auxiliary systems like lighting, etc. They all consume power, and together that is the total facility power. And then you have the IT power, which is the actual consumption of the servers. So the goal of PUE is basically to show what proportion of electricity of the site is used only for the IT equipment. And you want to, in an ideal world, you will, like a mining site or data center, will consume all its power, will just flow directly into the servers. But that is not what is happening in reality. You also have some additional consumption of other things inside that mining facility that is required to get power delivered to these servers and cool them, etc. So PUE is just total facility power divided by IT power. This number will always be bigger than 1. Usually it's like a little bit bigger than 1, like an extremely good PUE is like 1.03, 1.05 is also quite good, and then you have 1.1, etc. Traditional data centers often have like 1.2 or 1.15. That means that they consume like 20% additional power on other cooling or power losses, etc., on top of the actual consumption of the servers. So this is PUE is a very, very much used metric in the conventional data center industry and has been for a very long time. Interestingly enough, in Bitcoin mining, PUE is even more important because mining is even more cost competitive than conventional data centers, but I still have not seen any public miners talk about what their power usage effectiveness is. So this is a very important metric, and it's just going to become more important in mining, more used as mining converges with the broader data center industry. So I will show you now an example of how power is flowing through a mining site so that you can understand how power usage effectiveness is actually calculated. So let's start from the beginning, and we will go through the journey of the electron from transmission grid to chip. Basically, it all starts on the grid unless you generate your own electricity for mining, but we assume now that everything starts on the grid. Then there is a substation that steps down the voltage from the grid, and this here is outside the site scope. So the miner is just getting the electricity delivered from the substation. So the miner is not responsible for the substation in this case, but in some miners, they own their own substation, but it's not so common. So the miner is buying electricity here, 100 megawatt in our example. That electricity flows through the main site transformer that is used to step down the voltage. That main site transformer in our example has a 0.8% power loss. So inside transformers, there is some power being lost in there. through various means. And then, so there's 100 megawatt going in to that transformer, outcoming 99.2 megawatt. So we see already a little bit is lost here. Then we have the medium voltage switch gear. Power need to flow through that as well. And here you have like 0.2% loss in our example. And then you have go down to only 99 megawatt. So you already lost 1% just by power flowing through these components here. And then power is distributed from that medium voltage switchgear to several distribution transformers. Like these transformers usually power either one container alone or two mining containers, or like they basically power one transformer, distribution transformer, power a zone of miners. And that transformer might have 1% loss. So then we are at 98 megawatt. Then we have a low voltage switch gear. So that could be one switch gear for the mining container, etc. That is 0.2% loss in our example. So then you have 97.8 megawatt left. And then you need to use some of the power for cooling and to cool down these chips. So let's say you spend 3% of the power on cooling, then you're down to 94.8 megawatt that you can use for mining. And then you have auxiliary systems, like you have to have lighting in the site, etc. 0.1% loss, 94.7 megawatt left. Then mining is flowing from the switchgear into the power distribution unit. So one of these is basically delivering power, distributing power to several miners in the racks. That is a 0.4% loss in our example. And then we only have 94.3 megawatt left. And this is where the power is reaching the IT load or the IT component. So power usage effectiveness is calculated with that 94.3 megawatt in our example that is going into the miner's power supply unit. So everything that from my power is coming into that power supply unit, that's the IT load in our example. And it's important to also realize, I added it to our example here, that the power supply unit also has a quite large IT loss, or quite large power loss, I mean. It has I would say, the largest of all these components here. In our example, we use 3%. That is a part of the IT power, so it's not really a loss, but it's still power that is not coming into the chips. So in our example here, 100 megawatt going into the site, but only 91.3 megawatt gets through into the chips and can actually produce the hash rate. So what is the power usage effectiveness of this site? It's 100 megawatt, which is the total IT load, the total load that is delivered to the site, divided by 94.3, which is the power that is going into the power supply unit of the IT equipment. So then you have 1.06. So we see that 6% more power is used just to deliver power to the chips and cool the chips, then 6% of the power is just going to that. And it's important to remember that in this example, I didn't account for any losses in cables. So all these yellow lines here are cables. So power is flowing in cables. And there is also some losses going in the cables as well. And also this is just purely an example, like all these different losses on the different hair components can vary significantly. I will explain more later why they can vary. So here is how power usage effectiveness varies between sites. There are three structural drivers of power usage effectiveness. First, you have the climate impact. That is the biggest factor. And the climate sets a thermodynamic floor for cooling efficiency. So in hotter temperatures, you have to spend more electricity for cooling. There is no question about that. And then the second is infrastructure quality. So if you purchase like low quality infrastructure, usually it will have bigger power losses. So one of the drivers of the price of infrastructure is the like low power loss infrastructure have usually higher price, better components, etc. And then the design of the site. So basically the design of the site, it is something that you can do in a smart way to make the best out of the infrastructure that you buy and the climate that is on the site. So this one can be extremely much leveraged, and it can be extremely big differences between the bad site designs and good site designs. Some site designs are so bad that even in good climates with good infrastructure, they might still have give a high power usage effectiveness, while the opposite can also be true. So first one is climate. We will go through all these three now, first starting with climate. The climate sets the thermodynamic floor for cooling efficiency and sets a floor for power usage effectiveness. So in a hot environment, you will spend a significant amount of power on cooling. There is no way to avoid that. In a cold environment, you are very lucky. You can use the cold air for free cooling, and you don't have to run much active cooling, which consumes power. So this climate is a structural flaw in the power usage effectiveness. Important thing to realize is that 100 megawatt of power in means 100 megawatt of heat is also generated throughout that site. So that means that like you have to just get rid of that heat, or in an ideal scenario even reuse it, but you have to get rid of that heat. And there are basically two ways to do that. You can use passive cooling, or you can use, which is you don't spend any electricity on the cooling, or you can use active cooling, where you use like fans or pumps or whatever to pump around stuff, air or water to cool. And there is also, of course, different degrees of variability on how hard you run the cooling. So as you can see, like here in Middle East, India, parts of Africa, Southeast Asia, like around the equator, it's really hot, and therefore there is little mining going on there. Like let's say the Middle East, they have a lot of electricity, but cooling is just so difficult in that desert environment that yeah, you really have to have extremely cheap electricity to make up for that cooling problems. Like, first of all, it's an engineering problem. Yeah, you can solve that. But there is, as I said, there is a structural flaw on the power usage effectiveness because of the climate. So that means that a mining site in UAE or Oman or whatever, it will always have a much higher power usage effectiveness, or much worse power usage effectiveness than a mining site in Norway, even though they might have spent much more on the infrastructure and spent much more time on the site design, etc. So, and this is why, like, most mining sites are concentrated in the northern hemisphere. Like, I don't know how big percentage of the hash rate is here, but it's extremely big. Then we have infrastructure quality, impact on power usage effectiveness. So the quality of the infrastructure is to determine how efficiently power is delivered and how heat is removed. So as I showed, there is power losses in each of these components, also in the cables. You have two types of infrastructure in mining. You have electrical infrastructure and cooling infrastructure. When it comes to electrical, transformers, switchgear, etc., they all have losses when power goes through them. The question is just how big power losses they have. There's different between different of this electrical infrastructure. Some transformers lose more of the power in the form of heat, for example, than others. Then you have cooling. Some pumps consume more electricity. Some fans consume more electricity. Like there is there is always some differences here. And as well, like we can also talk about air versus hydro versus immersion. So air cooling, that's, I would say it's a less efficient way of cooling because you have to you'd like just pumping air through the machines. With direct to chip hydro cooling, you can actually directly and more precisely cool the machine, and thereby you can avoid that some of this air is to like kind of wasted and not really used for cooling. Having uneven cooling of the machines, etc. So cooling infrastructure is really impacting the power usage effectiveness. Like if you construct an air cooling site poorly, you might need to use extremely many fans and water curtains, etc. for the cooling. So hydro cooling usually has a lower power usage effectiveness than the air cooling sites. And then it's important to remember that this is an investment in infrastructure. So like a lot of investments, it's just a question of CapEx versus OpEx. Do you want to pay more now to save more money in the long term, or do you want to pay less now and pay more in the long term? So if you have like a long-term mining project, you want it to run for many, many years, it might make sense to spend on the infrastructure. But if you're just planning to mine a couple of years and then move on, then you might be able to get away with buying a cheaper infrastructure and accepting that higher power usage effectiveness. So site design also has a big impact, and this is actually something you can affect quite, you can affect it if you do good engineering and etc. and construction. So site design is optimizing how efficiently the infrastructure that you bought is operating. And you can, for example, have differences in airflow pathing. Where is that heat being transported? How is it circulating around? How much do you need to run the fans in order to recirculate that air? You can do thermal separation, which is standard in all mining sites right now. You can set some space between different equipment, and also important to design the power path layout correctly. General principle is to have as little cables as possible to make these paths as short as possible. And you need to optimize the transformers. Like there is a lot of things you need to do in the design phase. And you have important realization is that two sites with identical infrastructure can operate at different power usage effectiveness levels purely due to design efficiency. And here you see the two archetypes of Bitcoin mining site design. You have the purpose-built site, and then you have the containerized site. So purpose-built sites can usually get a bit better power usage effectiveness because you can purposefully build it, adapt it exactly according to your requirement, to the climate where you are, etc., to your infrastructure. While a containerized site, you often just get the containers, and then you can, of course, you have to adapt the containers, etc. But yeah. And here are some realistic power usage effectiveness ranges. In scenario 1, with cold climate plus high quality infrastructure and design, all the three factors are basically very optimized. Then you can have 1.03 to 1.05. That's a good power usage effectiveness. In a scenario 2, you might have 1.05 to 1.1. And in scenario 3, 1.1 and above. And there are many mining sites who have 1.1 and above. And that can be fine in hot climates. I'm not saying they are bad sites, but it's still, the point is that they will consume a lot of extra electricity on that cooling and power losses, etc. So let's go through how power usage effectiveness actually changes the mining economics. We will now compare between a site that has 1.05 and 1.15. In site A, the power price is 4 cents, and site B as well. Total facility power is 100 megawatt. both these sites get exactly the same power delivered, then the ASIC power, like the IT load, is 95.2 on site A and 87 on site B. That is the result of that higher power usage effectiveness. It spends a significant amount of that power just on the other things than the actual mining, while site A spends less. You can remember that calculation that I did earlier. So yeah, other power, 13 megawatt for other things, 4.8. And then assuming, this example assumes that there is a 30% net profit margin on mining using S21 Pro, hash price of $40 per petahash. I made this example before Bitcoin price fell. So we can make a cost of that non-mining load, like a direct cost. And we see here it's 1.7 million per year for a 100 megawatt site, just to pay for all that electricity that is used for non-mining purposes. So 4.8 megawatts run at 100% over 1 year at 4 cents, that's 1.7 million. So that's what they're spending just on other power consumption than the direct mining. And of course, that is necessary to keep the miners running, but you don't want to spend too much on that. Meanwhile, site B, it consumes 3 times as much power on, 3 times as much money on non-mining activities as site A, just because it has a much worse power usage effectiveness. It spends 4.6 million is just going into the other electrical infrastructure on the site. That is 2.9 million less of profits for that site per year. So I also calculated what is the lost profit or alternative cost of using that power for non-mining activities. That is basically the direct cost plus the lost profit from that. So that is what they lose. That is 2.2 million, 6 million. And you see here hash rate. Site A produces much more hash rate than site B, about 500 petahash more, because it has more megawatts to use on the mining than site B. The hash cost also, because all that cost that is required to run 100 megawatt of power need to be included in the hash cost calculation. And we see here that site A has a lower hash cost than site B, and that means that site A is more sustainable long term. It has a little bit more room to withstand bear market environments than site B. Not much, but a little bit. And then effective power price, that is the USD divided by the kilowatt hours consumed by the whole site, basically. So not only the mining site, because the power price for each kilowatt hour sent into the ASICs, basically. So the site pays for 100 megawatts, but only 95.2 is actually used by the machines. So the machines, the effective power price that each machine is consuming based on that power that is actually delivered is 4.2 cents. So we see it started at 4, then it's like 4.2 for power actually delivered. Meanwhile, for site B, it's 4.6 cents per kilowatt hour. So you see here, they were very happy. We have 4 cents in Texas. We are very proud of that. But then it ended up at 4.6 just because they have to spend so much power on cooling and everything else. So it can have a big difference. All that extra power you spend on cooling, on power losses, etc., it can have a huge difference and make your effective power price actually quite much higher. Cost to revenue ratio, site B is 0.41, site A is 0.38. So we see here there is also some difference, and this means this is because site A is more, it can withstand bear market a little bit better than site B. So site A makes more money and it is less risky to run than site B at the same time. So that's the advantage of having a lower power usage effectiveness. How can miners optimize power usage effectiveness? So this goes into the 3 factors determining power usage effectiveness that I mentioned: climate, infrastructure, and site design. So in order for miners to optimize power usage effectiveness, they have to optimize these 3 factors. First, they can choose a good location, a cold place. Cold climate reduces the need for active cooling. So start mining in Norway or in some other northern country, Canada, for example. By the way, we have a big mining opportunity in Canada if anyone are interested, with natural gas to mining. So yeah, start mining in a cold place. Avoid the hot places, or at least know that if you choose a hot place, you will spend a lot of electricity on the cooling, which makes your project less competitive. Then you have to, or you can choose to do long-term infra investment. So as I said, if you invest more now, then you can pay less you can consume less power later. You have a better power usage effectiveness of your site. OpEx versus CapEx trade-off. Then you should employ some great engineers and do some smart site design. Don't rush in site design. I've seen how that plays out. It doesn't look good. You should really respect the site design phase. Site need to be optimized for the climate and conditions of the place it is inside and the infrastructure that you want to have on that site. So site design is important. So these 3 factors you should use to optimize the power usage effectiveness. Key takeaways. The first one is quite obvious, yet it is often forgotten in the mining industry. Mining machines effectively consume more power than their nameplate. The second one is that hot climates carry an invisible electricity penalty. In hot climates, you will pay for more electricity just for cooling. Cheap infrastructure often means higher long-term costs. High power usage effectiveness reduces usable mining capacity. So, and this is particularly important in the era we are entering with a scarcity of powered land and grid connections. So if you have 100 megawatt allocation and you worked like for many months or years to finally get that power allocation from the grid company, and then does it really make sense to spend 10 of that 100 megawatts just on cooling and on bad design and on bad infrastructure? No, because power is very scarce. You really want to squeeze out as much as you can from that power. So don't make these mistakes. Get the power usage effectiveness optimized so that you can use more of that scarce power that you have on the site. And this last point is to be cautious of sites where power usage effectiveness is not economically prioritized. This is like everything in the world. Sites in developing countries where people don't really want to invest so much money, they usually have worse power usage effectiveness. They don't prioritize so much to invest in that infrastructure. While sites in, let's say, Norway or in the US, they are more viewed as a long-term investment, and they usually have better infrastructure, at least, which can reduce the power usage effectiveness. So just to be aware of that as well. And if you're looking to buy a mining site, you always need to know what is the power usage effectiveness, how efficient is that site, and that need to reflect the price you're willing to pay, of course. So yeah, thank you very much for watching. Don't forget to like and subscribe to our YouTube channel and subscribe to our newsletter at hashlabs.io/insights. Goodbye.